Hi there. Good morning. I'm Dan Frost. I'm the president of the European Association of Geochemistry. I hope you're all enjoying the meeting. It's my great privilege to introduce the 2025 EAG Science Innovation Medal Lecture. So the EAG Science Innovation Award, I think the name is very clear. It recognizes scientists who have made a particularly important and innovative breakthrough in our field. This award celebrates not only outstanding research excellence, but also significant contributions to the broader scientific community. It honors those whose innovative work is advancing the field of geochemistry and inspiring the next generation of young scientists. So it's my privilege to present the 2025 Science Innovation Award to Christine Putnis, a true pioneer and inspiring role model for early career scientists. So please join me in congratulating Christine.
One more time, please.
Yeah, I hope that applause comes out on that photograph, because that would be really good. So Christine received her medal in the plenary session on Monday, and now I'd like to welcome Mike Hochella to tell us more about Christine and the wonderful contributions that have earned her this prestigious award.
Thanks, Dan, very much. Wow, Christine, I don't know if you saw, but the room is packed. Congratulations. It is my distinct and great honor and privilege to be the citationist for Professor Dr. Christine Putnis for the 2025 Werner Stum Science Innovation Award of the EAG. Sue Brantley, Sue's right here, from Penn State in the U.S., Encarne Ruiz Angundo. Encarne's not here. Oh, she is there. Hi, Encarne. I'm sorry, I haven't seen you yet. From the University of Granada in Spain. And I put this nomination together. First, allow me to read just one sentence from the support letter of Encarne, which so perfectly speaks for all three of us. Quote, Professor Putnis has been a tireless advocate for the geochemistry of the mineral fluid interface and has made some of the most significant scientific advances in the field of the last few decades, with the theory of coupled dissolution precipitation being a particular standout contribution that would not have been possible without her outstanding talent for atomic force microscopy and in situ experiments. From Sue and my points of view, Christine, and I'm sure many of you also in this audience, Christine's work goes far beyond what she specifically studied, and that's the mark of great science. The processes that Christine has discovered can be mapped into other spaces, and those spaces become influential in all of many fields, including the geochemical cycling of the elements, the formation of clays and iron oxides, soil development, microbial community development, hydrothermal alteration, diagenesis and metamorphism, and even ore deposit formation. Importantly, Dr. Putnis should be celebrated for another reason. She chose to raise a family of six children, all of whom are now, in some cases, long-term professionals, but now all professionals, including 4 doctors and surgeons, a leading partner of a very large law firm that has international reach, and even an exceptional computer and IT technologist. I know that Christine and Andrew are very proud of all of them, as they should be. I know them all. My family knows them all. And now with multiple grandchildren, the Putnises, they're here to stay. As a result, and this is the reason I even mention this, as a result, she started her central and core research career very late compared to nearly all of us. She obtained her PhD in 2006, less than 20 years ago, and yet she has still been able to gain this remarkable scientific presence with exceptional impact. Lastly, I have a slide to show. EAG's Science Innovation Award, as Dan so well knows, is named in part for Werner Stumm, who unfortunately passed away, as you see there, in 1999. Werner is arguably the most famous and impactful water and interface chemist who lived in the second half of the 20th century. I can say that for many reasons, but I think the most important reason is that in the 1980s he won the Tyler Prize, which is known as the Nobel Prize of Environmental Science. Werner and I overlapped at Stanford in the early 1990s when he was on sabbatical there, finishing up the book that you see here, Chemistry of the Solid Water Interface. It turns out he chose one of our lab's iron oxide atomic resolution scanning probe microscope images, happens to be a scanning tunneling microscope image, for the cover, taken the same year as the publication of this book in 1992. And very much like one of Christine's AFM images of these highly reactive monoatomic steps that Christine has explored exhaustively on any number of minerals and other materials, along with countless other surface features, all in an exceptionally wide array of aqueous solutions, and better probably than anyone has ever done or been able to do. You can imagine what Werner would have thought of Christine's work. I need to add that Werner was a huge supporter of women in science in his day, and I saw this and witnessed it time and time again, personally. I can say with certainty that if he were here today, he would be the happiest person in the world to see Christine win this award bearing his name. Ladies and gentlemen, I present to you the winner of the 2025 EAR Science Innovation Award, Professor Dr. Christine Putnis.
Citation, I hardly recognize the person that you were talking about, but I'm very thankful, very grateful, and actually overwhelmed to receive this award, which is a huge honor, especially as it celebrates Werner Stumm, whose work was exceptional, and among many other things that he did, he showed that the weathering of minerals is related to the surface charge and in other words, the composition of the fluid at the interface. And that's very inspiring for the work that we've carried out since then. I want to also say a little bit about Michael Hochella, because he came to Münster when we were working. He came in 1998 on a Fulbright fellowship, and we worked together. He opened my eyes in that year to the nano world, and I don't think I've left there ever since. As you'll see from my talk, I'm working at the nanoscale. It's very exciting, and that was the introduction to my working at that level, including being able to work on the atomic force microscope. As well as with Mike, of course, I couldn't have done any of the work that I've done without the support of exceptional people. I've been so lucky to have wonderful students. Rather than calling out names, I've put a list here. I hope I haven't forgotten anyone, but I've had a lot of wonderful students. Above all, it's been great fun, and that's what I think science has to be. You have to be passionate about what you're doing and really enjoy it. So I've had a huge privilege of being able to work with all of these people, and I don't think at the end I've put Andrew's name, because I've worked together with my husband. I may want to make a special mention to Li Junwang He was a fantastic scientist. Sadly, he died in 2021. We spent many, many wonderful hours together on the AFM, and I owe an enormous debt of gratitude to Lidrum for his inspiration. Right. Right. I'm talking about the mineral fluid interface, of course, where minerals react with the environment. I'm talking about a huge area, and I want to also add the understanding mechanism, that we understand the mechanism at the nanoscale, and what can we learn about the large scale from the nanoscale, because it's making that link that's important for us. I'm going to show you, my talk is a historical overview. It's not just centered on specific experiments, therefore it is rather superficial, but I wanted to show you the original experiments that I did more than 20 years ago that gave us the beginning of an understanding of a mechanism that will govern the reactions at the mineral fluid interface. I took a very small, you can see the size there, potassium bromide crystal, 2 by 5 millimeters, and I'm going to add a solution of saturated potassium chloride to the surface of that little crystal, but not covering the surface. So what you're going to see immediately now is, you'll see the fluid comes onto the surface, you'll see a bright ring. That's just reflection of the light from the surface. Look at the crystal and how it behaves. Uh-oh. What do I have to do that? Okay, so the fluid, we're looking down on the top of the crystal, 2 by 2 here, more or less. And you see that there is a white rim. It is a very sharp interface between the pale color and the original, which is a transparent crystal. And it proceeds to go through the crystal, which is being changed to a new composition, and the crystal remains the same original size. It's free to change because it's in an open system. And we keep going till the whole crystal of the original KBr is replaced by a crystal of KCl, pure end members of a solid solution. So what we want to do is work out what is happening here. The replacement is cloudy or white because it's highly porous. Right. If we look at the surface in SEM, that's what we see. The right-hand side is a zoom-in of the left-hand side. And the porosity is even taking on the cubic form of the original salt crystals. And this continues all the way through the crystal. I'm going to show you another view now where I've glued that crystal, the KBr, between 4 glass slides with glue so that I'm restricting where the fluid can go. I'm going to drop the fluid into the top of, I've made like a little tube out of glass slides, and it's a saturated KCl solution. I've given the conditions there, and let's see what happens. I need to do that again. Again. Okay, a double space. Okay, you saw the fluid coming down. Here we go. There's the interface. There's the cloudy new composition, highly porous. How do we know it's highly porous? Well, we saw from the SEM, but have a look now. It's going to drop out through the bottom. There it goes. And then the top of the liquid will come down. There it comes. It's crystallized on the outside of my glass as big as it moved up. We have, again, the same as the first experiment, a new composition, and it's a KCl composition. We have, I've stopped it just in case it didn't work. So you can see where I've stopped the film, and you can see the progression. It took about 2 hours, to reach the KCl composition. This is in 40 hours. Oh, the first one was 2 hours. This is 40 hours of filming. This was all done in the early part of after 2000. So it's a long time ago now, but this is what we've used as the basis of trying to understand what is happening. So here the analysis of the solid phase is very clear. Start off with pure KCl. There's the X-ray, powder X-ray diffraction peak, and then we move across until we get pure CL. And the intermediate phases along the solid solution KBr, KCl range. So that was the solid composition. What about the fluid? What's happening to the fluid? In Japan, I was working with Katsumoto and his group in Tohoku University in Sendai, and I was able to use their phase shift, real-time phase shift interferometry to have a look at the fluid changes at the interface. As soon as I press the next film, we'll see the fluid immediately touching the surface. So there we go. Back. Return off. That way. That way. Okay, there we go. Have a look at the way these lines are representing the refractive index of in the solution, so it's the solution composition. Don't worry about the lines, except the distance indicates a change in composition. As soon as that fluid touched the surface, there was a huge compositional change at the surface. Out there in the bulk, it takes longer to change. As time goes by, I've put the lines in there to the right. That's the crystal on the right-hand side. Oh, here we go again. It's cycling. And if I go on to the next one, you see the solution is moving through the crystal as the reaction proceeds. And there we go. In the end, we have a different fluid composition from what we started with. Okay, so how are we using that to try to understand more real situations? And as you've heard, my main research has been in atomic force microscopy. Here is a cleaved surface of calcite. I've done a lot of work with calcite. And here is a 5x5 image. Left-hand side is height, right-hand side is deflection. They're the same surface. We often use the deflection image because it looks nicer, but the left-hand image, the height image, gives us the information in the Z direction, and you can see the height here was set at 15 nanometers. So it's truly on a nanoscale in the Z direction. Okay, so I'm just going to add water to that surface. There we go. That's after 1 minute, I think. I'm scanning at about a minute, a scan. For these experiments, and it's a rather large area, 5x5, but as soon as pure water touches the surface, we get dissolution. And you can see there's characteristic etch pits. Look at the top right-hand corner. There's a big deep one there. Etch pits are probably forming at defects anyway, but that is a bigger defect or maybe a threading dislocation. And so it changes as we go by. The etch pits spread. Dissolution occurs by the movement or the retreat of the step edges, and we went from almost a homogeneous flat surface to now a very complex energy landscape. So this is where we overlap with the work of Andres and his group, that we don't have one dissolution rate here if we were going to really analyze what's happening there. Dissolution is very different all over the surface. So we're getting dissolution, the release of, in this case, calcium and carbonate over the surface. It's going to be different all over the surface. So the mineral fluid boundary layer is going to have a different composition across the surface of, there's the last image there, across the surface of that calcite. Now, what about growth? So we can see the difference. The top ABC growth steps on calcite, and you can see down the bottom there's a little growth island getting bigger and bigger. This is a time sequence going from left to right. If we're lucky, and very often we are, we get beautiful spiral growth, probably initiated at defects, but probably threading dislocations in the structure. No natural mineral is going to be entirely perfect or pure. And so you can see that the spiral growth is the form of growth if the solution is supersaturated with respect to calcium carbonate. Okay, look at this one. A and B is a zoom in of A. I put a saturated solution. It's not supersaturated, it's saturated. It's fluid that was equilibrated with calcium carbonate powder. I immediately get nanoparticles, but nanoparticles not all over the surface, only in particular orientations, and those orientations along these step edges, which are dissolving, or on etch pit sides. Image number C is after a few hours, where those nanoparticles are merging along particular crystallographic directions, and then in D, a zoom in again, and we can see that the nanoparticles, you can almost see the nanoparticles there, but they're merging, getting straight lines, and the straight lines always make us think we're undergoing crystallization. E and F is an interesting couple of images. It was published by Carlos Rodriguez Navarro, and that was where I put a saturated calcium hydroxide solution on the surface. Immediately, it was really exciting. Immediately in number E, I had little particles, little nanoparticles all over the surface. And within a couple of hours, they'd merged, and we were getting straight sides, and we ended up with little rhombohedra of calcite on the surface. But these are all experiments, not with a supersaturated solution. So what's happening here? Before I go on to that, I'm going to look at calcite growth in the presence of selenium, because that's related. Okay, there's another lovely spiral on calcite with a calcite growth solution. Let me see if I can get this to go. I'm going to add the growth solution plus the selenium in ppm amounts. I'll show you in the next slide. And we have a beautiful spiral whose shape changes, and we get the formation of a lovely heart. One side is being pinned. We were so excited about seeing the heart, we were neglecting the fact that all of these merged nanoparticles were blocking the surface. And then when we added, you can see from the bottom, we add the solution, we take it away. We add the solution, we get the nanoparticles, and we take it away. And we get the dominant growth from the supersaturated solution with calcite. Okay, I've stopped that film so that you can see the progression there from the first growth of the supersaturated solution. On we go until we get to the last image, and we see nanoparticles together with a distorted normal spiral growth. The distortion is most likely because of incorporation of selenium ions in various positions on that pyramid. Okay, what if we don't have a growth solution and we just add ppm amounts of selenium on the surface, which is what I did. So there we have dissolution of the calcite in number A. If we have a look at the next images, we've got nanoparticles over the surface. Nanoparticles specifically in areas of very fast dissolution, not all over the surface. Eventually, they merge and cover the surface. But here, the bulk solution is undersaturated with respect to any possible precipitating phase. Oh, again, go back. Oh, that one there. Can we get crystal growth from undersaturated bulk solutions? Normally, we can't get crystal growth unless we're supersaturated. So we can't avoid the thermodynamics. Supersaturation, and we have the images got lost, is related to the ion activity product and the solubility of that particular phase. We have to have that greater than 1. So the ion activity product has got to be higher. Otherwise, we're not going to get any kind of growth. If for calcite, the example would be the ions in solution of calcium and carbonate have to be greater than the solubility product constant. Okay, here's another example. We've got calcite dissolving again. This is a bigger section. It's 10 by 10. I'm adding here a solution, 50 millimole of ammonium phosphate. I've also done it with sodium phosphate. But I'm totally undersaturated with respect to any phase. The little rhombohedral edge pitch looks smaller because it's a bigger area, but the Z direction is still on the nanoscale. You can see some little nanoparticles there, and this should run. Let me do that again. Yeah, here we go. The edge pits are spreading. You can see that there's dissolution, but we're getting nanoparticles and formed all over the surface. And once we've got one nanoparticle, we get more in the merging together with other nanoparticles. Sometimes they form and dissolve. Sometimes they do this and end up covering the whole surface, and we have the formation of a new phase, and this is a new phase of a, oh, no, we're doing it again. There we go. I've stopped this film as well so that we can see A, B, C, the progression. This is happening within about 2 hours. And the number G is after a day where the nanoparticles have merged, so it's a different orientation here because I took it out and put it back in. The nanoparticles have merged and we're getting straight edges. We're getting the formation of a new crystalline phase on the surface. Is this just a superficial reaction? Look at the number H. This is where I took a little crystal of calcite, I put it in exactly the same solution, made a section, looked in the SEM, in backscatter SEM, and you see an interface, just like with my salt solutions. The calcite is pseudomorphed in a new phase. It's a phosphate phase, a calcium phosphate, and after a few days, it actually does end up being a carbonated apatite. So we've got the original pseudomorph formation of a new crystal composition. Okay. This is jumping up to more closer to the future. This was some work of a doctoral student of mine where she was looking at cadmium on a calcite surface. We get the similar kind of thing. So you can see the formation of nanoparticles where we've got a small amount in millimoles of a cadmium solution on the surface, and we end up with the surface being covered with a new phase, and at the end it's a cadmium carbonate phase, ottovite, which in fact actually covers the surface, and the reaction goes much more slowly after that. So we've looked at a lot of toxic elements because a lot of our work is looking at how can we sequester, how can we, from solution, toxic elements. So this is a lot of work that I've done together with François Renard, who's now in Oslo. You can see here we've looked at selenium, which I showed you the images of. We've looked at antimony and arsenic and various other surfaces. The main thing to see here, together with dissolution, we're getting the formation of nanoparticles in specific places on the surface. Those specific places are where dissolution is fastest. Okay, so we can summarize that, and here I've drawn a little, it could be any crystal, any mineral, but it looks like calcite because it's rhombohedral. We have a solution containing element C, or ion C. The mineral, for example, calcite AB, is calcium carbonate. In that fine fluid layer at the interface, we're getting the release of calcium carbonate ions, and we're getting the formation. If we can supersaturate with respect to a new phase, it could be calcium and an anionic species, such as arsenic or selenium, or it could be, for example, cadmium carbonate if C is a cationic species. So dependent on the fluid composition right at the interface, but also right at the interface, we have, as we saw from the dissolution, we have a very inhomogeneous, a heterogeneous surface. So we are able to supersaturate in specific positions on that surface. Okay, how can we relate this to other things apart from toxic element sequestration? I took a brucite surface, and this is work with Jörn Hovelman, looking at carbonated water on brucite. Brucite is magnesium hydroxide, and it's a weathering product, or a product of olivine weathering. And here again, we've got the height image on the left and the deflection image on the right. That's brucite dissolving. Lovely triangular etch pits. Different all over the surface because we have different dissolution rates across the surface. And when we add or dissolution, we add the carbonated water. All I did was to bubble CO2 into pure water. Within a few minutes, the pH had gone down to about 4. I pass that over the surface because, of course, I'm working in a fluid cell in the AFM. We get nanoparticles, and you can see the triangular edges of the original etch pits are now covered with nanoparticles, which merge together to form a larger form, and very often at the ends of the etch pits, there are etch pits there that you can see, and if we zoom into that in number C, the circle there, we can still see that the nanoparticles are clumping or merging together to form a new phase, which we've analyzed in SEM, EDX, and the base there is the brucite, magnesium with only the carbon of the coating, magnesium hydroxide, whereas the nanoparticle phase, the merging nanoparticle phase, is magnesium carbonate, because you can see the higher carbon peak there. So this is an example of what happens during CO2 sequestration. We have to have available ions, cations, at the surface to form a new carbonate phase. Okay. The mechanism of leach layer formation during weathering, these processes are often called leaching, substitution. There's always words for them, but of course we would call it dissolution and precipitation. This has worked together with Encarni Rizzagudo. It's been published in twice now in geology. We took wollastonite, a very simple silicate, because we're wanting to look at a whole range of minerals to see if this process is holding. And so you can see A is the dissolving surface of the wollastonite. Once the solution goes on the surface, then B, C, and D is showing a progression, a time sequence of the formation of the nanoparticles which are merging on the surface, and that new phase is silica. So this is what's called the leached layers during chemical weathering of silicate minerals. Albertization. So now I'm going to take you into a much bigger area, into the field, just to show that it applies to lots of situations. And of course, albertization, which you probably all know, is very often associated with ore formation. This is albertization in the Cunnamunna area, north of Adelaide in South Australia. It's a huge area, about 300 kilometers in diameter. It's associated with the huge mineralization of Broken Hill. So there's a lot of element mobilization, a lot of ore formation in this area. Look at the interfaces. There's a pinkish one, that's albite, and it's almost pure albite. The gray one, in fact, in this case, is a potassium feldspar, also containing a lot of other elements. But in the field, when you see interfaces, there's a kind of indication maybe some kind of replacement reaction has taken place. There are just a couple more images to show the scale of the interfaces that we were observing. And if we have a look at, this was a hand specimen that I took, and I actually did work across those interfaces, which on a nanoscale are actually very sharp between the albite and the K feldspar. But we've reproduced these kind of experiments in the lab. If we have a feldspar structure, we've also used oxygen-18 to trace the water, because it's a fantastic way of finding out where the oxygen is going. We could say this is a substitution experiment, that we're taking out the calcium, for example, and putting in sodium in the structure. Very simple, ion exchange. Solid state diffusion, probably. So these are the experiments that we did with the starting material. We did it both with oligoclase and with labradorite, but here's this first one with oligoclase. There's the composition. The experiments were done at 600 degrees and at 300 degrees in pressurized autoclaves. Here is a SEM image of the reaction, which maybe you can't see very well. There's a very sharp interface of albite, which is 99.6, is virtually almost pure albite, sodium aluminosilicate. In the center is the original material, but that interface is very sharp, which I will show more images of. So the TEM is enabled us to look closely at that interface. The interface is sharp on a chemical scale, but it's wavy. It's not a straight line, but compositionally it's very sharp. The rim looks rather turbulent. That's because it's highly porous. And the original phase did have pores, but not pores at the scale that we could see as well as in the albite. So again, during these replacements, we're looking at the porosity formation associated with the formation of the new phase. There's a TEM cut again. That's a zoom in of that interface. Albite, almost pure on the left, plagioclase, the original plagioclase on the right. And so we've done a lot more work on this, chemical analyses. we can show that it's not just forming sodium albite, the sodium plagioclase, but I don't like this showing lots of numbers, but if you look at the left-hand column, you can see that there are a lot of elements were present in the original oligoclase and the labradorite. That was from the natural samples. After the experiment in the oligoclase, you can see the albite. We have almost lost all of those elements. Where are they? That we have also shown through oxygen 18 that the oxygen ends up in the silica and aluminum oxide tetrahedra, and the only way that you can do that is to break all bonds. If the oxygen 18 is going to end up in the new structure, at that interface, we've got complete dissolution followed by reprecipitation of the new phase. And all of those elements that were originally present are now in solution at the interface, ready to be transported somewhere else by diffusion through the fluid phase, and when conditions change, chemically or physically, they may be deposited somewhere else. So this is the basis of ore formation, that from elements that were originally, did I miss one? Yeah, I did. I think it's that one. Yeah. So how does an understanding at the nanoscale lead to a clearer understanding at the larger scale processes? So I've written here that these are all of the issues that we can try to understand by knowing the mechanism of what's happening at the mineral fluid interface. Environmental remediation, as you've seen from all those toxic elements that I was able to show, ended up in the new phase. If we had a barrier of calcium carbonate across streams or whatever that were contaminated, we could sequester the toxic elements in a new phase, and this would happen actually quite quickly in terms of days. What I'm doing is in terms of minutes. Element mobilization, as we saw from the experiments with the plagioclases. Natural processes such as sedimentary rock formation, metamorphosis, metasomatism, and weathering all involved the dissolution of the original phase and the precipitation of a new phase. I'm going to summarize this by these little schematic crystal. A is the original crystal. The solution contacts the surface just by the dissolution of a few nano layers of that original crystal. We may supersaturate the fluid at the interface with a new phase, with respect to a new phase. Doesn't matter what's in the ocean, in the fluid away from the surface. It's that fine layer at the interface that controls the whole process. And that will be very different because of dissolution compared to the original solution. And then we progressively go through. I can go on to the next one. As this is happening, we have the formation of a porosity in the new product phase. Porosity generation depends on both molar volume differences between the product, the parent and the product, but it also depends, and maybe more importantly, on the activity or the solubility differences between the product and the parent phase at the interface. In the solution at the interface, we tend to think of dissolution rates, but they're also in water. This is the solution at the interface, which is different from the bulk. And the best way of doing this is with isotopic tracing, and I failed to tell you that with the original experiments all those years ago, we enriched the potassium chloride solution with potassium 40. So we knew that the potassium from the solution ended up in the new solid phase, just as the oxygen in the plagioclase experiments from the solution ended up in the aluminosilicate structure of the new phase. So this is what we called a interface-coupled dissolution precipitation, because it's all happening at that very, very fine level at the interface. It will be different thicknesses of an interfacial fluid depending on the situation, but we're initiating it with initial dissolution. So we're talking about almost on a sub-nanoscale level is where the reaction begins. And once the reaction can begin, it tends to keep going. And we see this, although we're relying on molar volume changes between parent and product and on reactivity or solubility differences, we see these kind of reactions happening all the time. So all of my experiments with AFM, I'm really excited because I'm always getting nanoparticles. So just as I was introduced to the nano world, I've never left it since Michael Hochella came to work in Münster, because nanoparticles are everywhere in the environment. And I just put down a list of recent publications because although I started with a historical overview more than 20 years ago, there are a few papers that we have at present. I'm going to, I don't know how much time I've got.
2 minutes.
Almost there we go. Again, I have not done any of this work entirely alone, and I owe enormous thanks to a whole lot of people. It's not necessarily in a list of priority, but Nkani has spent a lot of time with me, getting excited about images that we see. François, Helen, Christina, Torsten, Julian, Gail, because I was working in Perth, and we were looking at simulations of the reactions. Håkon Austerheim for his field work, and of course Michael Hochella for introducing me to the nano world. Andrew, of course, I can't leave him off. I think he was almost as excited as I was, but maybe not entirely. But he did tolerate my enthusiasm. And again, Li Jun Wang, I did many experiments with him. He was an exceptional scientist. I'm still working with his group in Wuhan, and it was a pleasure to work with all of these people that I've worked with. I think I've been exceptionally lucky, and also exceptionally lucky to have this honor of this award. So thank you all very much, and I'm happy to have questions.